Hi, everyone. This talk I'll be giving today is on a brief introduction to causal inference. There's a whole course I give titled Introduction to Causal Inference that you can go to after this talk if you want to at causalcourse.com. But this talk is just meant to give you some motivation and intuition for kind of the beginning of causal inference. It's like a high level of the first few weeks of the course. So you're not meant to get a complete understanding. If you want a like more in-depth understanding, that would be over a few lectures in the first weeks of the course. And then connections to machine learning, like out of distribution generalization, those come later in that course. So you can see the course and the book associated with it at causalcourse.com. This is like the first talk in the course that's meant to help motivate things. All right. So what is causal inference? We'll start with, and it's basically just inferring the effects of any treatment, policy, or intervention. So as an example, say you have a treatment and you want to measure how effective it is at treating a disease, or you have a policy to try to reduce emissions. You might be interested in the causal effect of that policy or different policies. And you could say you want to know the effects of social media on mental health. Just generally, anytime you have some X that you think might cause changes in a Y, causal inference is about measuring how Y changes in response to changes in X. So this talk will have 4 parts, and I'll pause for questions at the end of each part. So feel free to ask questions, and I'll be happy to take those at the end of each part. The first part is meant to just kind of motivate why causality is important. So basically, we'll see that for a key decision, causality is important for making that decision properly. And then the second part, we'll see, okay, correlation does not imply causation. You might have heard this before. Maybe I'll give you a bit more on that you haven't seen before. And then if correlation doesn't imply causation, and we're interested in causation, then what does imply causation? That would be the third part. And the final part, we'll see causation in observational studies. So observational studies are just when you observe some data. You're not running an experiment, but you find some data and you're trying to infer some causal effect using that data. So it's a very common use case for causal inference. All right. So with that, let's get into the first section, this motivating example. We will look at a purely hypothetical example, COVID-27. Say you have this new disease, and there's 2 treatments out for the disease, treatment A and treatment B. And let's say that it's your job to choose the treatment for your country. So it's kind of an important decision. And here I'll denote A with 0 and B with 1 in the coming slides. And let's say that you also have data not just on treatments that people have taken in the past. So these treatments are out there, and you have data on the treatments that people are taking, and you have data on the condition they have at the time of treatment. So if they have a more mild or severe condition. And then you have data on their outcomes, so if they live or die. All of these things will be binary variables just to make the example simpler. All right. So say that 16% of people who take treatment A die, and 19% of people who take treatment B die. In this case, it kind of looks like maybe treatment A is better than treatment B, but let's say that we were to zoom in and also look at their condition. So if we stratify the groups based on mild condition and severe condition, then we see that actually in the mild group, a lower proportion of people who take treatment B die. So only 15% die who take treatment B and 15% who take treatment A. And it's the same in the severe group. A lower proportion of people die who take treatment B. And so these numbers I have here, basically the denominator is just the total number of people who take who fall into that group, take treatment A and have mild condition, and then the numerator is the number of people who die. Okay, so this is an example of Simpson's paradox that you might have heard of before, just to illustrate that this is that the calculations are right here. I'm just showing the calculation, and and so for this first line, it's just the denominator comes from the number of people who take treatment A, so that's 1400 plus 100. That's what these denominators are, and the numerators are just the relevant conditions, and that multiplied by their mortality numbers for people with that condition. That's how I get this 16% here, and then same for treatment B. Okay, so this is one example of Simpson's paradox, but kind of the key thing that I want you to focus on here is that in this total column, we have that treatment A is the lower mortality rate, but then in the mild and severe column, so if we segment people based on their condition, then treatment B is the lower mortality rate. So, you have to choose which treatment should you choose. Is it treatment A or is it treatment B? And the spoiler here is that the treatment that you should choose, it depends on the causal structure of your problem. So in order to decide which treatment to choose, you have to know the causal structure of your problem. Okay, so I'll go into two scenarios. One where treatment B is the better one, and one where treatment A is the better one. So scenario one, where treatment B is the treatment you should choose. Here I just have the table from the last slide. In this scenario, basically it's where your data is generated in such a way where T is generated from the condition and not the other way around. So basically, C is a cause of T, T is not a cause of C, where C is the condition and T is treatment here. And then in the other scenario, it'll be flipped. Just to give you a bit of specifics about how this might work in this example, let's say that doctors are prescribing treatments based on the condition that they see people in. So here, treatment B is a more scarce treatment. So one thing I forgot to mention is just that fewer people are getting treatment B. So only 550 people get treatment B, whereas 1,500 people get treatment A. But so the doctor sees someone come in with a mild condition, and then they say, okay, they have a mild condition, so we'll give them less scarce treatment. Most people have mild condition, and so they give them treatment A most of the time. And then if they see someone that has a more severe condition, they might be more willing to give them the more scarce treatment, treatment B. Okay, so their condition here at the top is a cause of the treatment that they're given through this. The doctor is the mechanism that's allowing that. Okay, so in this kind of scenario, where the condition is a cause of treatment, and any other scenario you could imagine where a condition is a cause of treatment, you actually want to take treatment B. So you want to look at these numbers, the 10% and 20%, and those are the relevant numbers, not the 16% and 19% over here. So I'll get into why that's the case a bit more later in the talk, but just the portion of this talk is just to illustrate that causal structure is important. So, okay, just to recap, in scenario one, treatment B is the better one. And then in this second scenario that I'll look at, treatment A is the treatment that you should choose. So this scenario, all that's changed in this causal graph, so it's just saying what variables are causing other variables. In this scenario, T, the treatment, is a cause of the condition. That's the only thing that's changed. they're still both causes of the outcome, whether the person lives or dies. Okay, so some details for how this could work in this example is, say that you come into the office to be prescribed treatment, and let's say that because treatment B is more scarce, you have to wait a longer time, and your condition can worsen while you're waiting for treatment B. So basically, because treatment B is more scarce, it makes you wait longer, so your condition can get worse while you're waiting. So treatment here is at the time that you take the treatment. And then if you were to get treatment A, it's a less scarce treatment. It's abundantly available. So if you come in with mild condition, you'll still have your mild condition by the time you actually take the treatment. So in this scenario, where this is the general causal graph you need for this scenario, but this is one example in our setting, then you would actually prefer treatment A, not treatment B. So the key thing here is that causal structure, this causal graph, matters for which treatment you would want to take in this important decision. And that's the end of this motivating example section. So any questions about this?
Yeah, so I'm not seeing any questions so far. So maybe we can give people like a minute to write down the questions. And also, I should mention that Brady is taking questions after every section so that he can answer them in a more timely manner. So please go ahead, take this opportunity to ask questions about this motivating example. I see we already have a question, yes. So the first question is, not sure I understood the scenario with treatment A. How treatment can cause condition? Should I treat the scenario as only theoretical?
So the condition here is I should say, the condition you have at the time that you take the treatment. So say you were to come into the office with a mild condition, but then the condition that's being logged in the data isn't that condition at the time you come into the office, but the time that you actually take the treatment. So you come into the office and then you get prescribed treatment B, but you have to wait to actually get treatment B because it's a more scarce treatment. So while you're waiting, your condition worsens to severe. So the fact that you were prescribed treatment B has led you to have a severe condition. Whereas if you have treatment A, you might have stayed at a mild condition.
All right, we have one more question. In many cases, the actual graph is not known. How would you know that you have chosen the correct scenario?
So this is a more advanced topic, but there's ways you can try to infer the graph, which I won't cover in this talk, but it's covered in the course and book. And even when you can't infer the graph completely, you only get a partial graph. Say you don't get all the directions of the edges. There's kind of a frontier of research right now where they're trying to do causal inference in that setting, where they don't know all of the graph, but they know parts of the graph. And yeah, so I would look at some of that frontier research, but we won't see it here.
I think let's do one more, the last question, if that's okay with you, Pedro. Sorry, Brady.
Yeah.
Pedro is asking a question. In which sense the causal inference compares traditional correlation calculation? Yeah, I'm going to repeat the question. in which sense the causal inference compares, I guess, to traditional correlation calculations?
So if you just look at the kind of correlation or association between the treatment and the outcome, so T and Y, that's kind of like what this total column is. So let's see back here. So expected value of Y given T is a kind of correlation or association. That's what this total column is. And then when you stratify based on mild and severe, you're throwing in this variable that you're controlling for, C. So it's a more like fancy thing that when people say they're controlling for something, that's what it looks like. They're throwing it behind a conditioning bar here. And we'll see a bit more about this later in the talk. But this total column is kind of the naive correlation equals causation thing.
Yeah, thanks. That was the last question for this part. Let's move to the second part.
So to recap, the main thing from that last part was just that causal structure is important for decisions, and the last decision was an important decision. In this part, we'll see some details about correlation does not imply causation. So you might have heard this before in a statistics class if you've taken those. If you haven't heard this before, that's fine. I'm just going to give you a quick recap of what it is. So say that you notice that people who sleep with shoes on often wake up with a headache. So it seems that sleeping with shoes on and waking up with a headache are strongly correlated. Maybe you could think that you shouldn't sleep with shoes on because you'll wake up with a headache, and that it's causal, but it also might not be causal. It could just be that people who sleep with shoes on are sleeping with shoes on because they drank the night before, and then they're also waking up with a headache because they drank the night before, drank alcohol. And so in this sense, there's a common cause, drinking the night before, that's causing the two to be associated. So you're seeing this association between the two, or correlation between the two, because there's this common cause that's causing both of them. So there's two ways to think about, well, at least two, think about why the fact that they're associated doesn't mean that that it's a causal relationship. So one is that people who sleep with shoes on, shoe sleepers, they differ from non-shoe sleepers in a key way, and that key way has to do with this confounder. So the shoe sleepers are going to bed drunk, say, and the non-shoe sleepers are going to bed not drunk. So these two groups of people, they differ in a key way. Another way to look about it is this more graphical way that I have here in this graphic, where it's just that there's a confounder. So something that's causing both of them. And that confounder kind of allows, you can think of association flowing from the going to bed with shoes on to headache along this path through this confounder. All right. So really what you're interested in is causal association. So there's not an arrow there in this case, but that's what causal inference is trying to detect, is this arrow directly from the treatment, in this case sleeping with shoes on, to the outcome, waking up with a headache. And you can think of total association that you measure. So that's if you were to just look at the expected value of Y given T, or the correlation between Y and T, you can think of that as a mixture of causal association, which is this blue line, and confounding association, the red line in this picture. And the word association just means statistical dependence. Depending on who you talk to, correlation, they might say correlation is technically, it's a linear form of statistical dependence, but colloquially, people often use correlation synonymously with association. So I'll be using the word association more, I think, because it's less ambiguous. All right, so that's how you can have that's an illustration of why correlation is not imply causation. But one kind of tangent here is that we, as humans, we use correlation equals causation all the time. It's a cognitive bias. So say in this example, rather than having shoe sleeping as the treatment here, we just have some star. So just whatever you think might cause a headache, and then a confounder of that star and headache. So we can generate this star, like in our heads, when we're trying to explain our headache, via another cognitive bias known as the availability heuristic. So it's just whatever is most available in our head, whatever happens to occur to us in the moment. The bias there is that stuff that is available in our head is important. Like we should think of that as maybe relevant for the thing we're thinking about, the headache in this case. And so say you have a headache and you're trying to explain why. Like, why do I have this headache? You might come up with some star to explain your headache via the availability heuristic, or motivated reasoning is another one. So say that I don't like spending time with my in-laws, my parents-in-law, say, then I might say, oh, okay, well, I noticed that I have headaches whenever I hang out with my parents-in-law, so I'm trying to give a reason for why not to spend time with my parents-in-law. And then, so we could say that this star explains the headache via correlation equals causation cognitive bias. So just noticing that the two are related. Whenever I hang out with my parents-in-law, I get a headache. So it must be that hanging out with them is causing my headache. Okay, so this is just a slide about cognitive biases that we're probably making the correlation equals causation cognitive bias all over the place. Even people like me who study this topic. And here's an example. So we have basically in red, we have the number of people who are drowned by falling into a pool each year. And then in black, we have the number of films that Nicolas Cage appears in. And the x-axis is time here. So this is a fun one. I guess maybe Nicolas Cage is driving people to drown themselves. And if you want to see more of these, they're at this website. They have all these spurious correlations. Okay. So that's the kind of the end of the correlation does not imply causation section. So we could take any questions about that section if there are any.
I think we are at the same situation. People, let's give people a minute to write the questions.
And as a reminder, for if you ever have a question while I'm going through a section, feel free to just put it in the chat then. I think we'll continue on to the next section then.
All right, so no questions yet. I guess you can cover both questions from this portion on the next Q&A, right?
Okay, so correlation doesn't imply causation. But then the question is, then what does imply causation? We're interested in, we need to know when things cause other things. When is a treatment for COVID-27 actually effective against COVID-27? When is something to deal with headaches actually effective against headaches or preventing headaches? We need to know these questions. We need to know the answers to these questions. So that's what this section is about. What does imply causation? And I'll have to introduce a concept that you might have not seen before. if you're not familiar with causal inference, which is the concept of potential outcomes. So it might take a bit of time to wrap your head around. I'll try to help with that. So say you're inferring the effect of some treatment or policy on some outcome. So let's just take this headache case that we were just looking at. So we want to know that the outcome is headache or not headache. You have a headache or it goes away. So you want to know some treatment to get your headache to go away. And let's say that if you were to take a pill, then your headache would go away. You're happy in this picture. And if you didn't take that pill, then you would still have your headache. So if this were the case, so we're kind of talking about two hypotheticals here. What would happen if I were to take the pill? What would happen if I didn't take the pill? If this is the case, that you would have a headache if you didn't take the pill, and then your headache would go away if you did take the pill, then we would say that there's a causal effect, that the pill is causing you, it is a causal effect on headaches. But if it were the case that when I don't take the pill, my headache would still go away, then we would say there's no causal effect, right? So whether or not I took the pill, my headache still went away. Okay, so there's kind of this key thing here is like, what is the outcome? What is the potential outcome that I would observe if I were to take the treatment or not take the treatment? So this is the intuition for potential outcomes. I'll introduce a bit of notation for it on this slide. So another way of denoting that you've taken the pill is this do t equals 1 or do 2 equals 0. That's the kind of stuff you would see in Yuta Pearl's notation. So your outcome, given that you do t equals 1, that you take the pill, this is a way you could denote a potential outcome. Where I here is basically talking about a specific individual. So so specifically for me, that's what the I here denotes. Or a specific unit is another word you'll see. And then you'd have the same thing down here. It's just the do t equals 0 is changed. So it's like, what is your potential outcome evaluated at when you take the treatment or when you don't take the treatment? And this is commonly denoted, so this is potential outcome notation. One way of doing potential outcome notation is just yi with a 1 in parentheses, and then the bottom one, yi with 0 in parentheses. So that's the potential outcome under no treatment and the potential outcome if you were to take the treatment. So, given these definitions for potential outcome, then you can just write down the causal effect as just this difference between the two. So if it's the case that when I take the treatment, my headache goes away, so I get a 1 for my outcome. So 1 is headache goes away, 0 is I still have my headache. If it's the case that when I take the treatment, the headache goes away, and when I don't take the treatment, the pill, then my headache stays there, then I could plug those into this causal effect here, and I get that there is a causal effect. The causal effect is 1. It would have been 0 if the guy were happy here. So if yi0 were a 1, then the causal effect would be 0. There'd be no causal effect. Okay. So we've just introduced potential outcomes, the intuition and some notation for it. But there's this problem known as the fundamental problem of causal inference associated with this. So what that is that say I were to not take the pill. So I have a headache, but I decide I don't want to take the pill for whatever reason. Then I would observe that I still have my headache. I would observe yi0 equals 0. But I would not be able to observe what would have happened had I not taken what would have happened had I taken the pill. Okay, so this top one, yi1, is counterfactual because it's counter to fact. The fact was that I didn't take the pill. What would have happened had I taken the pill is counter to fact. Okay, so since I don't observe yi1, then I can't calculate the causal effect because we're missing that yi1. And then similarly, if I were, say I did take the pill, then the other one would have been a counterfactual. So if I do take the pill, then yi1, I would observe equals 1, but I would not observe yi0. Say it is the case that yi0 equals 0, but I don't get to observe it because I chose to take the pill. So I still can't calculate the causal effect. So you might be thinking, well, I could just one day I'll take the pill, the next day I won't take the pill. And basically you'd be making some assumptions if you want to do causal inference in that case. But the main assumption is just that you're assuming that you're in the same state on the day that you take the pill and on the day that you don't take the pill, right? There's all these other factors, stuff going on in your body, stuff going on outside your body, and you're assuming that those are all kind of the same, controlled for, which is hard to do. Okay, so we have this fundamental problem, causal inference. How do we do causal inference when we have this fundamental problem? Well, so first, what I showed you just now, this difference is called the individual treatment effect. And you could just take the average of those. So it'll be clear why I'm doing this in a second, but say you took an expectation of this, then you get the average treatment effect. By linearity of expectation, you just have this, the average of the difference is the difference of the averages. And then the key thing is that these two quantities are not equal. So if we've observed some data on y and t, we can calculate, or we can estimate, these conditional expectations. But we can't necessarily estimate these expected values of these of these potential outcomes. So the reason that these two aren't equal is just correlation does not imply causation. So if you look at this graphic, some graphical intuition for that is that this top quantity is a purely causal quantity, right? We're looking at the potential outcomes. So it's blue here for this causal association. And then the bottom quantity is a combination of causal and confounding association. So I put blue and red here for that, it's measuring effectively the association flowing along both of these paths from t to y, t to c to y, and t to y. Okay, so key thing here, these two quantities are in general not equal, but there's a kind of a special thing that can make them equal, and that's randomized controlled trials. So here's just copy and pasted from the last slide that these two quantities aren't equal. Well, with a randomized controlled trial, it actually eliminates the confounding association. So this confounding association is gone in a randomized controlled trial. Okay, what's going on there? Why is that the case? Well, one way of looking at it is that, I haven't said what a randomized controlled trial is. A randomized controlled trial is when you, say you're deciding to give the pill or give a placebo pill, like not give the pill. You flip a coin to decide for a given person whether they get the pill or not, if they're in the treatment group or the control group. So because it's a coin that you're flipping to decide the treatment, that means that the treatment is not determined by any confounders. So T can't have any causal parents because the only thing it's determined by is the coin. Like you could write that the coin is a causal parent. It's determining the treatment, but T isn't going to be determining anything else unless you choose to determine the outcome via a coin flip as well. I don't know how you would do that, but don't do that. You only determine the treatment from the coin flip. And so since that's the only thing affecting the treatment, then T can't have any causal parents. So there's no confounder here. C is not a confounder, it's just a cause of Y. Okay, so that's one way of looking at why randomized control trials are very special, why they eliminate confounding association. Another way of looking at it is that basically it makes the treatment group and the control group comparable. So in the shoe sleepers example, we had that the people who were waking up, or the people who were falling asleep with their shoes on, a lot of those people were going to bed drunk after having drank a lot of alcohol. Okay, so that's very different from the people who were going to sleep without their shoes on. Those people were going to bed without drinking alcohol. Well, if you were to, you could imagine going into people's rooms while they're just about to sleep, and you could like take their shoes off or put shoes on them randomly by a coin flip. That's how you would turn that into a randomized control trial. And then you'd make it so that you have roughly the same number of people who are going to sleep with shoes on after you've done your intervention. Roughly the same number of those people went to sleep after drinking a lot of alcohol, and then roughly the same number of people who don't have shoes on went to sleep after drinking a lot of alcohol. They're comparable groups. Okay, so what happens when you have this? So that's kind of two ways to think about how randomized control trials eliminate association, or eliminate confounding association. The first one is this graphical one. The second one is kind of just thinking about comparable groups. It's not really graphical. When you have this, then you have that these two quantities are equal. Okay, so in general, they're not equal, but when there's no confounding, like in randomized control trials, then they are equal. Okay, so that completes this then what does imply causation section. So any questions about this section?
We have one question. It might be more related to the previous one, but still going to read it. So sleeping with shoes can be an indicator of drinking the night before. If you want to know when you will have headaches, aren't sleeping with shoes and drinking kind of being the same for this prediction?
Yeah, so you're talking, basically it sounds like the question is like, how can I predict when I'll have when certain people will have headaches? And so association is kind of the same as predictive ability. So if two variables are strongly associated, then one of those variables is very predictive of the other and vice versa. So if you just care about prediction, which you might, then association is what you'd care about. Imagine though in this setting though that so you have one society where like two different populations, like a transfer learning type problem. So one society, it's not normal to sleep with shoes on, and then you have another society where it is normal to sleep with shoes on. Then what you learn about shoe sleeping's association with headaches in the society where it's not normal to sleep with shoes on, so you see that they're very associated, could be completely wrong in the society where it's already normal to sleep with shoes on. Then the two might be not associated at all. So yeah, so basically, like when you look at transfer learning, that association might disappear in a different population. But yeah, for causal inference, you want to just know the causal effect. So it's like, what would happen if I were to sleep with shoes on? Would it cause me to have a headache? It's basically when you want to decide what actions you'll take, which is like we're always deciding what actions we'll take. When you're in that setting, you want to know what the effects of those actions will be. You want to know what those actions will cause. You don't want to just know what they're associated with in the population, because it might not be that they actually cause those things. They're just associated, and you don't have the confounder that actually leads you to the outcome.
All right. No more questions at this point, so I think we can continue.
All right. So as a recap, we just saw that correlation does not imply causation, and then in the last section that how you could get causation. One example is with randomized control trials. Another example, another setting is, what if you can't do a randomized control trial, right? So you can't go in and randomize the treatment. You can't go into people's rooms and flip a coin to decide whether you're going to put shoes on them or take their shoes off. Or so you just have data that you've observed. That's an observational study where you can't do an intervention. So, in the ideal case, you would have intervened on the treatment. You would have randomized the treatment so that you don't have any confounding, right? There's no confounding when you randomize the treatment. Everything will work out well. As correlation equals causation, or association equals causation in a randomized control trial. But in observational studies, you might have this confounding because you're not randomizing treatment, you're just observing some data. And why can't we always randomize treatment? Well, for example, there might be ethical reasons. So even if you're even if you have the willpower to randomize treatment, there's reasons why you can't do it. So say you want to measure the effect of smoking on lung cancer. For most people, you can't just randomize people to smoke or not smoke. I mean, maybe if you're like a dictator, you might be able to, but like ethically, you might not want to do that. There's also an infeasibility reason. So say you wanted to measure the effect of different like governance systems, or economic systems. So say communist, capitalist, you want to measure the effect of that on gross domestic product. Well, you can't just, it's like really hard to be able to randomize whole countries into an economic system. You can't just say, okay, well, you're going to be a communist country, you'll be a capitalist country. Unless you're a dictator of the world, I guess. And then there's cases where it's just impossible. Like there is no way you could do this. So say you wanted to measure the effect of of a specific gene at birth, right? So you're born with this genetic code, and then you go through life where you have these environmental factors influencing things as well, not just your genes. So say you want to measure the effect of a specific gene at birth on breast cancer. Well, after a person's already been born, you can't like go back and change their DNA. So in the future, you might imagine that maybe we can change people's DNA, but after they're already born, say you can't go back and change their DNA at birth because they were already born. So maybe you could change their DNA when they're alive, but their DNA at birth is the thing you care about because of these environmental factors, and you can't do that short of a time machine. So say you can't get a time machine, say like those are impossible, then it would be impossible to randomize that gene. So how do we measure causal effects in observational studies, given that we can't always do randomized control trials? And you might have heard the words adjust or control for confounders. So that's all you do. So you basically have to adjust or control for the right variables. So we'll call them W here. And if W is a sufficient adjustment set, I'll give you some examples of what that might be, and you can see it more about that in the course. But if W is a sufficient adjustment set, so it's the things you want to adjust for, then you have this. So you have this potential outcome where we've conditioned on the sufficient adjustment set. And then you could also write this with this do notation. There are two different notations for it. But these two quantities, the same quantity, are equal to this quantity that's purely statistical. It doesn't have any causal notion to it. So it doesn't have a do in it. It doesn't have a potential outcome in it. It's just the conditional expectation of y given t comma w. So if you have a sufficient adjustment set, you get this. So another way of saying this is like association equals causation if you've conditioned on this sufficient adjustment set. And so in this graph here, C would be a sufficient adjustment set. So if we condition on that, then you can think of it as blocking this confounding association. It blocks it when you condition on C there, which is the singleton variable in this singleton set W. Okay, so I'm not going to explain like why you can think of it that way. That's just kind of the graphical intuition. And you can also just do a proof with this kind of stuff without the graphs. But say you don't want to condition on W, then all you do is just the same thing. You get the same quantity, but then you just put an outer expectation over W. You just sum over W. So it's not, it's not too much more complicated if you don't want to, if you're not interested in quantities where you're conditioning on W. You just sum over it, W. The sufficient adjustment set. So let's see some more examples of sufficient adjustment sets. Basically, all they do is they block confounding association. So graphically, so we just saw this one, we could condition on C and that blocks the confounding association. And the shaded nodes, I'll show some sets that are more than one variable. So shaded nodes are examples of sufficient adjustment sets, W. So in this graph, say we were to condition on C, but then also on another variable to block that other path that confounding association flows along. So here W2, and then it would be blocked at W2, or if we condition on W1, it would be blocked at W1. And you could throw in more variables like W3, it's still blocked at W1 graphically. This is how I think of it in my head. Okay, so these are good because then you've isolated the causal association. When you've blocked all the confounding association, then the total association will just be causal association. And just to like tell you, you have to be a bit careful about this stuff. There are examples where you have variables up here above these other variables, and you don't want to condition on them. So like when you have this kind of V structure, or an immorality is another name for it, because Z1 and Z3 have a child together, but they're not connected. In that case, you don't have to condition on Z2 because the association is already blocked by this kind of special causal structure, and you actually don't want to condition on Z2. It would open back up this path. It would make confounding association flow. So I'm not going to go into that, but there's just a little complexity there that you can see more about in the course. Okay, so to finish off, we will just look at this COVID-27 example again. So this table is the same table from that slide. And we're going to be looking at specifically the case where causal graph is this. So that was scenario 1. So what is the new thing we have? It's that we have this formula for how to make it so that association is causation, right? So we have this purely associative quantity here, and then we can get this causal quantity from that. That's the new thing we have in our arsenal. Okay, so what are the variables we need to control for? What's a sufficient adjustment set? It's just C. And the way we would calculate this is we just sum over C. So I've just taken this expectation over C. I just sum over it and multiply by the probability of C. That's just writing out that expectation for a discrete variable C, which in this case is discrete, right? It only took on the values of 0 and 1. Mild condition is 0, and 1 is severe condition. All right, so armed with this, we can now calculate this sort of causal quantity. So this is scenario 1. In scenario 2, the calculation would look different. You wouldn't control for C. So, now that we calculate this quasi-quantities, we see that, okay, treatment B is the better one, given that we're in scenario 1. And so all we've done is just plugged into this formula just to give the calculation for that, just to kind of illustrate what's going on. Say you first look at this mild column, okay? So you want to get the probability that you have mild condition. That's the first thing we'll multiply by. And that's just the number of people who have mild condition divided by the total number of people, okay? So if I add up these 4 denominators, 1,450, 500, 100, I get 2,050. And then if I calculate the number of people who have mild condition, it's just 1,400 times 50. So that's what's in the numerator there. Okay, so this is just probability of having mild condition. Same thing down here. And I'm just multiplying that by the mortality rate, which is mortality rate, that's this quantity, expected value of y given t comma c. So it's the mortality rate for that specific treatment and condition. So it's that cell in the table. Okay, I probably should have shown that earlier, but okay, so it's the same thing for the severe column, right? So you still have the same denominators, but now you have 600 in the numerator because 100 plus 500. And then same for these. Okay, so yeah, so looking at this formula, this sum it's these two terms because C is binary. That's why the sum is turned into just two terms, and that's how we calculated it. Okay, so the calculation for scenario 1 gives you the causal numbers that you would care about are these ones. And this is how we calculated them. The naive calculation, so that's how you calculate the total column, which we saw earlier. I'm just going to put it back there. We're not going to go through it, but it's the same calculation we went through earlier. The total column is just these numbers. And it turns out, actually, the total column is the one you would look at if you were in scenario 2. Yeah, so, welcome to Causal Inference. That's the end of the talk. You can see these slides at the website if you want to see the slides. And yeah, thank you. So any questions about this last section?
Yeah, so we have quite a few questions. Let's start with the first one. Could you give an example of sufficient adjustment, aka W?
Can I show my slides again? I think they just, all right. So let me do a faster way. So basically, in this causal graph, C here is a sufficient adjustment set because it blocks this confounding association when you condition on C. In this graph, you have these confounding associations going along these two paths. One example of a sufficient adjustment set in this path is W2 and C, right? And you could have also taken out W2 and just put in W1. Okay, so these shaded nodes are the sets. And then in this graph, it's just an empty set in the graph on the right, say. So okay, maybe the question wasn't about the graphs. Say it was about like what these variables are. So in the COVID example, C is the condition. So mild or severe, and that's what C is in that example.
So moving to the next question. Theophilus is asking, You said that we could add the flip of a coin to the causal graph in case of randomized control trials. What keeps us from extending the graph by adding extra parent nodes with respect to the treatment in the same fashion without treatment controlled for?
Okay, so it sounds like you're talking about making other variables causes of treatment. And I might misunderstand the question, but you could do that. You could basically, if you're in control of the treatment, you can make treatment a function of whatever you want to make it a function of. And so whatever you make it a function of will be the new parents of T in that graph you do.
Right. Let's move to the next one. Dmitry is asking, what would you suggest as a resource to continue learning about causal inference, specifically for industry applications?
Mm-hmm. Yeah, so most books are written by academics, right? They're not written by industry people. So like if you want a solid understanding of the topic, you can read books. But if you're only interested in applications, I'm not super sure. There are probably applications books out there, but I'm not as familiar with them. I use causal inference in applications, but yeah, sorry, I don't know.
What about your book?
Yeah, well, so you could use my book in industry application. I'm guessing this person might have seen my book, and maybe I don't know if they haven't seen my book. I would recommend my book. Of course, I wrote it. It's at causalcourse.com, but there might be like okay, there is a book that I talked to some. I'm forgetting his name. There is a book out there, a guy who was writing a book where he uses it. He uses it at. He's been worked at multiple companies, and like I think he currently works at Barclays, the credit company, I think, and he's written a book, but I don't think it's out yet, and I don't know what it's called.
All right, it's not too easy to find, but I guess maybe if you remember the name or of the person or the book, could you post it on Slack?
Yeah, I can definitely do that.
Amazing. Yeah, moving to the next question. So what causality analysis technique or techniques would you recommend to start with for cross-sectional data? A bit of an explanation. Similarly, like Granger causality is the state of the art for time series data.
Well, so I don't think Granger causality is the state of the art for time series. So if you're talking about causal inference, like you're trying to infer causal effects, the book by Hernan and Robbins, at the end of their book, so these are two big guys in epidemiology, which they use causal inference there. That their book, at the end of it, the last part is all about causal inference in time series data. If you're interested in inferring the causal graph, right? So like what causes what, that's at the end of Elements of Causal Inference. So that's a book that's popular among machine learning people. So Jonas Peters is the first author on that book. At the end of their book, they do causal discovery in time series data. But yeah, Granger causality is I would not recommend that for causal discovery.
Okay. One more question, the last one. How do we decide on which variables are to be represented in the causal graph, given that we can conceive of continuum of events, or so it seems? For example, match catching on fire, sulfur on the match combining with oxygen. A bit of a tricky question, but maybe you got it.
So the events are continuous, or I didn't quite get it now.
Yeah, so let me try to read it again. I'm not sure I got it myself. How do we decide on which variables to be represented in the causal graph, given that we can conceive of a continuum of events. For example, match, as in, I guess, match to light a candle, catching on fire, sulfur on the match combining with oxygen.
Yeah. Okay. So, I don't know that much about chemistry, but like I imagine there's some chemical reaction taking place over time where these different elements are, decreasing in quantity and such. So you can represent, you can just take time and then have a variable at every time step. So you have to quantize time to do that, but you have to choose how you quantize it. But so you have those different variables that you mentioned at every time step, and sometimes you'll see people collapse time, and then they're only going to have a small number of variables, where time is not relevant in it. But you can unroll that into different subscripts for the variables at different time steps.